Okay, so we're gonna go over the quiz number 8. Go ahead and click on share. Okay, so minimize this one out the way. Okay, quiz number 8. Okay, so quiz number 8. So pretty much we're dealing with the resonance of the circuit. Okay, so number one, so they want number one, the resonant frequency based on this formulas right up here. 1 over the quantity 2 pi times the square root of LC. So that's what I show. That's what I show here. Okay, and then we put that into the equation and then do the calculation. That's give us over 400 over 4 million. Yeah, so 4 million hertz or 4 megahertz. Okay, so FR is 4 megahertz. And the next one, number 2, they want XL at resonant frequency. So XL at resonant frequency equals 2 pi times FR times L1. Okay, so that's 2 times 3.14 times 4 megahertz times 10 microhenry. And so we got, so that's 2 times 3 times 3.14. Okay, so, and then once we put that into the calculator and we calculate that, so XL comes up to 251. 251 ohms.
Only it's all yours.
Hey, mute the mics. Mute the mics.
Yeah, you're saying not here.
Okay, so let's get that. Okay, so number three, they want to find the XC at resonant frequency. So when they ask resonant frequency, XL and XC is equal to each other. You can do the calculation. So I did the calculation. It's still the numbers comes up to exactly the same thing, 251.3 ohms. Okay. If that is too, let me go ahead and take it that one a little bit bigger. Can you see that one a little bit better? Okay. Okay, so and then the next one, they want the ZT, impedance, total impedance. So total impedance equals ZT at FR. In this case, XL going to be canceled the XC, leave you what just with the R, with the RI. So this one right here, RI. So therefore, the impedance is going to be just 5 ohms. Okay, so any question, number 1, 2, or 3, or 4? Okay, so that's to do the calculation. Okay, any question on this? No question? Next one? Okay. Okay, so now we're looking, now we have to find the total current and the phase angles and the Q of the coil and the bandwidth, okay? So the total current, you can use the total current. It's going to be VT divided by ZT. VT, this one is 100 millivolt VRMS divided by 5 ohms. Okay, so that divided by 5, it should be come up to 20 milliamps. So the answer IT or I total, it'd be 20 milliamps. Okay, so phase angle. Now phase angles is going to be, so if you got the XL and XCs gets cancel out each other, leaving you just the RI. So RI doesn't have any phase angle. That's why it comes up to 0 degree. You can definitely put into the calculation and it would show you that will still come up to 0, okay? So the phase angles is R tangent of the quantity XL minus XC close parenthesis divided by RI. And if you do that, so XL minus XC, that would cancel each other. That leave you with 0 ohm divided by 5 ohm. So that's R tangent of 0, 0. That'll give you 0 degree. Okay. So the next thing you want to do, find the quality of the coil or the Q. Q equals XL divided by RI, okay? And we know that XL was 231.5 ohms divided by RI, which is 5 ohms. So you do that, and the result comes up to 50.27, okay? And there's no unit for that. Okay, so and then after that, we want to calculate the bandwidth. Bandwidth equals the resonant frequency divided by Q. So now the answer is going to be in kilohertz. So that's why I have to convert this one. I converted it to hertz and divided by that. That gives you in hertz form, and then convert it over into kilohertz. Kilohertz come to 79.57 kilohertz or 5.8. Okay, any question on number 5, 6, 7, or 8?
Yeah, kind of a question for bandwidth
Okay,
and bringing your final bandwidth value to a specific point value. Is the calculations more critical in finding the frequency for that bandwidth? Is it more exact to have the frequency clearer in finding the bandwidth, like say for a radio signal, by using that formula, or is there a different formula that doesn't?
this formula would give you pretty close to ideal. Okay, so we're talking about the ideal situation here. And then when we deal with inside when you do the actual things, that's when the application comes in. That's you have to take into the tolerance, whatever the tolerance is within the resistor, the inductors, and the capacitor. Okay, so right now when you do the calculation, it's based on ideal situation.
Thank you, sir.
You're welcome. Okay, any other question? All right, so next one. Okay, now they want to find the lower cutoff and the upper cutoff. Okay, so the lower cutoff is going to be the resonant frequency minus the bandwidth divided by 2. And the answer is going to be in kilohertz. So I can convert the 4 mega to 4 kilohertz or 4,000 kilohertz minus the 79.58 divided by 2. And you do that calculation, come to 3,962 kilohertz for the lower bandwidth or lower cutoff. Okay, and the upper cutoff is going to be at at resonant frequency plus bandwidth divided by 2. Okay, so that's going to be 4,000 kilohertz plus 79.58 divided by 2. That's come to 4,040 kilohertz for F2. The upper cutoff.
Hey, Sam, just real quick.
Yes, go ahead.
On our resonant frequency, we made that 4 megs. You agree?
Yes, we got 4 megs up here.
And what numbers look like we had for F1 and F2? Why didn't we leave those in like megs too?
Because the answer they want is in kilohertz.
Yeah, I understand that, but I'm just saying, wouldn't it have been better to say 3.96 megs and then 4.040 megs?
But the answer they want is in kilohertz.
All right, go ahead, move on, forget it.
Yeah, you wanted to convert everything to using the kilohertz form. So that
no, I understand that. I understand, but I'm just saying for consistency purposes, the resonant frequency was in megahertz, and this is just F1 and F2 to the left and right of the resonant frequency. So that, to me, just for consistency, it should be in megahertz as well. But no,
do whatever form that you think that it's easier for you. But at the end of the day, if whoever it is requests you to the answer form,
I got you.
And they don't want it in kilohertz, convert it to kilohertz for them. Okay. And for consistency, like you said, if you use megahertz, that's fine. You can do it in megahertz, and then after that, convert it to kilohertz at the end. Okay. All right, any other question on this number 9 or 10? Okay, no question. Next one. Okay, so now we got number 11, 12, and 13. So 11, 12, and 13. So they want to find the resonant frequency of the circuit here, okay? So we applying the formula that was given earlier at number 1. So resonant frequency equal to 1 over the quantity 2 pi and square root of the LC. So when you put that in and then you do calculation, that's come to 1,591.54 kilohertz, or just round it off, 1592 hertz. Okay, so now we want to find out what the impedance or the reactant of the inductor reactant. So you're going to be 2 pi times FR times L. And if you put into that, you put into the formula there and then calculate it, you should come up to 100 ohms at the end. Okay, so XL is 100 ohms. And then XC would be the same thing. Like I said, when it's at resonant, it's going to be equal to each other. Okay, now we want to do is to find the R coil. So the R coil, according to the formula, is right here. It's at XL divided by Q coil, okay? So XL, we know that it was 100 ohms divided by the Q coil. Q coil is right here. It's at 50, so 100 divided by 50. So that's leave you with 2 ohms. So therefore, this, so your little r, this R coil here is going to be 2 ohms, okay? So now they want a total impedance. Total impedance, you're going to take the resistance plus the R coil. So R plus R coil, which equals to 8 ohms plus 2 ohms equals 10 ohms. So that's your total impedance, would be 10 ohms. Okay, any question on number 11, 12, and 13, 14? Okay, you're good? Okay. All right, last 4 questions. Okay, last 4 questions, they want to find the total current. So total current at resonant frequency equal VT divided by ZT. So ZT or VT equals 10 volt divided by 10 ohms. So that's give you 1 amp. So 10 divided by 10 equals 1. Okay, they want inductive voltage, VL, and resonant frequency. So you're going to be taking the I total times XL, okay? So that's 1 amps times 100 ohms. That's come to 100 volt that goes into the inductor. And the capacitive voltage at resonant, it would be the same thing as it is in the inductor. So it's going to be 100, it's also going to be 100 volt. And then they want to find the bandwidth. So the bandwidth, it goes to FR divided by the Q coil. So we know that the bandwidth was 1592 or 1592 hertz divided by the 50. That should comes up to about 31.8 hertz. Okay. So any question on number 15, 16, 17, or 18?
All good.
Okay, very good. Okay, thank you, Mr. Pham. Back to you.
Okay, thank you.
You're welcome.
Okay. Hello, everyone. Before we started, do you have any question for me?
Did you clarify the week or the week should go today or this week, Mr. Pham? Just to clarify the schedule quick.
You guys take one get only today. Lecture with me. Tomorrow will be a take two. Okay? And take one will be on Tuesday and Wednesday with Mr. Tai. We have a no class on Thursday and Friday.
And then next week we're starting the lab classes. Is that correct?
Now that next week still be the same this week.
Same.
Yeah. The thing is, the instructor have to spend time with me to go up to the lab, try to do whatever we need and what the city requirement, what the supply do we need. That means too many things we have to do before the fall.
As far as mask regulations, have you received notification on that?
That's what I will be let you guys know.
All right, thank you.
The thing is right now, this week or next week, maybe not much coming. However, after next week, we'll be get more information. I don't, okay? And also, the Tech One final will be the last week of this month. We'll let you know in detail what day, what time. Okay? For now, I only talk to you guys. Make sure every student already done for electronic. That means last spring, AC this summer. Okay? And also you done for the tech number 2, the lab. Then you will get the certificate completion of this program. I don't care about the hour. Okay? That's out of my control for now. Okay, so any more questions? Otherwise, you must be download the handout in the website. Okay. For the final, what you need to review green number 1 up to green number 8 right now. And I believe you will be getting one more. That's it. If you understand all of the quiz and the question, then you don't have any problem. Okay? To pass, you have to get 70% or higher. That means C, okay? Minimum. Otherwise, if you want, I can get you make it up. Okay, so let me see. Set it into my iPad. Okay, so today we'll be talking about the transformer. And you understand it's just not much change. On measure, we already get through it. Okay, so if you're looking at the transformer here, simple here, okay, suppose two inductors are placed in close proximity to one another, but no electrical connection. Okay, it is them. Okay, suppose also that an AC voltage is applied to one of the inductor. And so the magnetic field surrounding the inductor with the applied voltage L1 here induce a voltage into other inductor. That means to get the voltage here. This phenomenon is known as mutual inductance. Inductor coils arranged in this manner result in common electrical device called a transformer. So that will be called a transformer. They transform from one voltage to the other voltage.
And Mr. Pham, how close would they have to be to do that? Because you said that you put two transformers in close proximity, and then you add a AC voltage to the other one, and when you do that, it induces a voltage or energy to the other one. But how close would they have to be for that to work? Like an inch, quarter of an inch, a half an inch? Or?
How I don't know exactly. Okay.
Oh, okay, thank you.
So I think that is the detail how to build a transformer.
Mm-hmm.
So let's see where we are now. Okay, here. The coil or winding with the applied voltage. That means when you apply voltage here, that's called primary. The coil that develop a voltage from the magnetic field. That's what they call a secondary. So when you're looking into the transformer, you're supposed to know which one is the primary and which one is secondary. The amount of the voltage induced in the secondary depends on the ratio of the turn of wire between two windings. So basically, how many turns, okay, to make the first one, and how many turns will be for the second one. That's why you're able to do a calculation. Now, in this figure, which coil or winding is primary, L1 or L2?
L1. L1 is primary. L2 would be, well, I stand corrected. The L2 is the one that's receiving the AC applied voltage.
Induced.
L1 is the primary.
L2 is the primary.
Yeah, L2 is the
L2 is the primary,
L2
and
is the
L1
primary.
is
L2 will be primary.
Primary.
Yeah,
One
L2
second.
is applied.
The thing is the applied voltage go to L2,
Right.
okay? And it is due the voltage go to L1. So L1 is secondary. That's just telling you the different symbol, okay? Above various transformer schematic symbol, the present or absent applied between the coil indicate the type of core used. If you're looking on this one here, iron core, ferrite core or air core. Okay, that's just for you to recognize. In this figure, show an iron core transformer with a tape secondary. You mean the tape right here. This tape may be used to alter the turn ratio between the two coils. Basically, the tape here. So that this transformer will be called center tap transformer. That means they divide secondary into two parts, one here and one here. They will be the same value, but they will be opposite. Okay? The turn ratio of transformer is a ratio between number of turns of wire on the primary. So they're using NP. That means how many turns of the primary. And they're using NF, how many turns of wire in the secondary. Okay, now on this transformer, primary 1,000 turns of wire. Secondary, they get 100. Okay, so they say 10 to 1. Okay, so that means if you take 100 divide 100, you get 10. Okay, and 100 divide 100, you get 1. A transformer with 1,000 turns on the primary and 100 turns on the secondary have a turn ratio of 10 to 1. So turn ratio NP over NF, 1,000 divided to 100, you get 10 turns, and there's only 1. The ratio between the voltage on the primary VP and the voltage on the secondary VF equal the turn ratio of the transformer. So if you get an NP over NF, they should be equal of V primary divided to VF. So from this formula, if you get the number of turns, you get the voltage at the primary, then you're able to calculate the voltage for the secondary. Okay?
Question, Mr. Brown?
Any question?
Yes, I have a question.
Yeah, go ahead.
Regarding the turns, the gauge of wire does have a factor for the voltage output regardless of the turns of the wire, correct?
Yeah.
So the turns can be almost not correct in the voltage in comparison to the winding versus the gauge of the wire and the coil, the how many times.
They have to be the same rate. You know, the same wire. It cannot be different, you know, between one, maybe 20 or 22. Yes. They have to be the same. Not supposed to be a different.
Thank you.
Okay, so for example, if there were 10 volts at the primary with a turn ratio of 10 to 1, then there would be 1 volt at the secondary. Okay, so you get 10 volts for the primary and the second will be 1 volt. So this is they apply this formula, NP over NF. equal VP over VF. Okay, transformer having a secondary voltage that is less than primary voltage. That's what they call a step down transformer. Okay, so VP 90 volt, VF only 30 volt. Okay, so basically it's a primary, okay, higher than secondary. That's what they call a step down. If a VP less than secondary, that is step up transformer. Okay, basically you must be memorize transformer is the device to converting from one voltage to the other voltage. Okay, so if the primary voltage higher than the secondary, that's what they call a step down transformer. Okay, and if we add higher than the VP, that will be step up transformer. A transformer having a secondary voltage that is greater than the primary voltage, that will be step up. Okay. If you get a question, you need to stop me. Okay. Let me know. Now, the tap of a center tap winding divide the number of turns in half. A transformer with 1,000 turns in primary and 500 in the secondary normally has a turn ratio 2:1. Okay. However, if the secondary has a center tap, the number of turns from the tap to one end of the secondary is only 250 turns. Okay, so that is very clear to you. If you get 1,000 turns here without the center tap, you get 500 turns. However, if you get a center tap, they divide 500 to 2. So that's why the first one you get 250, and the second one you get 250. Now a little more detail here. You get a 12 volt, 1,000 turn. Okay, and this is the whole thing 500, but they divide by 2. Okay, so 12 volt sideways to the primary of step down transformer result in 6 volt. That means from here to here, whole thing 6 volt. However, they get a center tap. They divide by 2. So you get 2 volt here and 2 volt here. They supposed to be same value. Only thing, make sure you understand, they will be opposite. Okay? If this sideways go up, this sideways will be going down. Normally, the center tap transformer got a lot of money. So if you don't want to using the center tap transformer, got too much with divide, we can using the same. Oh no.
Repeat the question again, Mr. Brown.
Question A, instead you using the center tap transformer. The thing it costs too much, but they can do the same thing like the center tap transformer. You know which device can do it?
What piece of equipment uses a center tap transformer?
Now, instead you using the center tap, I don't want a center tap. I can using another device,
Oh, what is similar? What is similar then?
similar, but it's much cheaper. Which device name? Who knows?
And works the same as a transformer?
Work the same at the center tap.
Same as a center tap. Sounds like a pot.
Huh.
It's the 4 diodes bridge.
Full rectifier?
Yeah. Bridge amplifier. Rectifier. You see, you remember in the electronic, right? You can get a full way rectifier. You can using the center tap transformer, or you can using a bridge rectifier. They do the same thing. However, in the bridge rectifier, you get only 4 diodes. One diode costs less than 50 cents. So they save a lot of money. So normally they don't want to using center tap. Only thing the people, the student already get through electronic last semester. And the new student for summer, then you will be learn that on next semester. Bridge rectifier. Okay, the current ratio is the inverse of the voltage and turn ratio. That is, if the voltage ratio increase, then the current ratio decrease. If the voltage ratio decrease, current ratio increase. So this is the formula they given to you. NP over NF equal VP over VF. And also will be equal IF over IP, not IP over IF. A transformer with a voltage and a turn ratio 10 to 1. At a second, there is current of 100 milliamp. What is the primary IP? So you're using the formula NP over NF equal IF over IP. Okay, so they want IP. Okay, then what IP equal? A or B or C?
A.
If you want to calculate IP equal NF times IF divide to NP.
It'd have to be A.
I don't know.
Ratio of tenths.
So you get 10 over 1, right? Equal IF over IP.
And the answer is B, 10
Exactly.
milliampere.
Exactly. If you're doing a calculation right, you can get 10 milliamp. So IF over IP equal 10 over 1. Okay? Then you can calculate the IP. That is very, very basic. So that's why I'm not doing calculation. But I can tell you that will be 10 milliamp. If the load IF, that means now you get the resistor here. That is the load. Across the secondary of a transformer, change decrease or increase in the resistance. The transformer automatically increase or decrease the primary current. This characteristic of automatic compensation is why a transformer is a self-regulating device. They're telling you if the load value here changes, then transformer will be automatic compensation. Okay. The power in the primary. If you want to calculate the power in the primary, okay, P equal IP times VAC, okay, V times I, but I have to be primary. Okay, secondary, P secondary, IF times RF. In practical transformer, however, the primary power in, can equal the secondary power out only when the transformer is 100% efficient, which only occur in an ideal transformer. After you measure the primary and the secondary power, you can calculate the efficiency of the transformer from the following equation. Okay, efficient percent equal PS divide PP, power of secondary divide power by primary times 100%. Okay, an ideal step down transformer with a voltage ratio 10:1 had input power equal 500 milliwatt. What is the power out? That means power of the secondary. Can you tell me? Do calculation telling me what A or B or C?
The answer is C, the same.
Okay, one answer C the same. Well, get a different or no? I think that you're up to this point. That means almost the end of this summer. I suppose you can do this calculation, no problem. Okay? The thing is that's a very, very basic thing.
The power is the same.
Okay. Now, this is the part, last part here. Transformer, L for impedance, matching. Now I get three circuitry A, B, and C. Okay, so now this is a generator, and this is a generator input or output resistance 50 ohm, and they connect the load 50 ohm, connect the load 25 ohm, and connect the load 75 ohm. What they want to calculate the load power for each resistance in the figure A, B, and C. Okay, and the formula to calculate the load equal V divide Ri plus RL square. Okay, and time RL. That's supposed to be RL. Okay, and now you do it for me for A, B, and C to see how many watt you get. And let me know. The first one, how many milliwatt? Get A right here. Who get the first answer?
Point zero four.
What's the number?
I'm gonna do it again, but I got 0.07.
Yeah, I got 0.01777. That is 1.7 milliwatt.
I'll try that again. 50 plus 25.
75.
75 squared
75 square is 5625.
times 25. It's 75 squared times 25.
No.
RI is 50 and RL is 25. So that's
That is
75.
75 square.
Right. And then times 25.
What?
Oh yeah, times 25. I forgot to do it. Yeah, that's correct.
Okay, I get 0.4 zeros, then 7, then all ones.
Well,
Mr. Pham,
I get 71.1 micro.
no, the RL is in denominator or in numerator?
you just apply into this formula.
No, the formula that's correct, but is RL in numerator or denominator?
Okay, now you can see. What we have,
The
And-
VS of it is 10 volts,
10 volt. Right?
right?
Divide 25 plus 50. Square time 25.
Oh, I thought only
Oh,
the
yeah.
denominator was squared. Yeah, that's what I thought. Yeah,
With the
okay.
formula that is given, I think so. It's, are we doing 10 over 75 whole square
Oh, the
or
whole-
just 10 square?
The whole thing is squared. I forgot that too. The way it's written in blue, I forgot.
Yeah, the way it's written in blue is confusing.
No, the answer is 444.4 milliwatts.
So 75.
444.4.
Purple and blue is not correct there.
Okay. Second, B.
$500 milliwatts.
Perfect. 500.
Yeah, yeah.
C, 480 milliwatts.
Perfect. 480.
Yeah, I think initially, everybody thought that the denominator only was squared, but that's not correct.
Yeah.
But the thing is, we cannot using the computer write this formula.
Yeah, yeah, I understand what you're saying, Mr. Bam. But that's what the problem was. People were thinking that the denominator only was squared, but that's not correct. The way you wrote it in red is the correct way, yeah.
Okay, so finally, you can see what they given to you 3 examples. Okay, so what they going to tell you? The maximum power you get a 500 milliwatt here. You get a 444.4. And you get 480.
When the impedance are the same.
Okay, so on this one here, you get the impedance 50 ohm and the load 50 ohm. That means they call matching impedance. Okay, That means the load supposed to be equal output impedance for the generator. Then you can get maximum.
Hey, Mr. Pham, so on letter B, like you said, is impedance matching because you got 50 and 50, but on letter A, you got 50 and 25, and letter C, you got 50 and 75. And those A and C, they don't match impedance wise.
Exactly.
Okay, yeah, I see it. See you
In
doing.
order to get the maximum power, impedance of the generator and impedance of the load have to be equal. Exactly, you get the amplifier. You connect that into the speaker. Then you have to know what the output impedance for your amplifier and the input impedance for your speaker in order to get the maximum power. Then they're supposed to be equal. Okay? If either one higher or less, you'll be missing. Okay? Missing power.
Hey, Mr. Pham?
Yeah.
It's not that big of a deal, but I think one thing that made your formula a little bit confusing, and you put the square term on, you needed one more parentheses. Because you got Ri plus R closed, and then you square it. But you got a parentheses on the front.
Sorry.
Yeah, you need one more parentheses, and that would
Correct.
yeah.
Thank you.
I
Yeah.
knew that. It's funny, the formula.
Yeah. If I do the same your guy do it. The thing it look like I plus R L square only.
Mm-hmm.
It's supposed to be square everything.
Right, exactly. You
Okay.
need one more parentheses on the end.
Yeah, thank you. Now, reflect impedance. If you're looking into this circuitry here, okay, you get the generator right here. And they connect you the transformer. Okay, what is the ratio for this transformer? Can you tell me?
53 to 1.
Yeah, 3.53
That's a step down.
to 1, step down. Okay, and they connect to the load for O. Okay, so basically what they want the maximum power will be go into the load. So that's why they're using the transformer. Okay, and the transformer primary here, this is primary, this is secondary. So they want to make the impedance, okay, of the primary, they want it to be 50 ohm. They matching with that 50 ohm, okay? And then they can calculate the voltage primary. That's easy for you to understand. 10 volt here, okay? Impedance 50-50. You can get primary on the transformer will be 5 volt. That is how to calculate the primary voltage. You get any question up to this point?
How you calculate the primary voltage? Did you apply the same formula Vs over R1 plus R2 whole square into RL?
Yeah. They're using the same formula.
Okay.
Okay, now, after you get the VP here, 5 volt, if you understand why you get a 5, the thing is you get a primary impedance 50 and the output impedance generator 50. So that basically divided by 2. So you get a 10 volt here. Divide by 2, you get 5 volt. And now you get a primary is 5 volt. You're able to calculate the secondary, okay, by 5 volt times 1 divided to 5.53, and that given you 1.14 volt. Okay, so in here they said the impedance reflect back into the primary of the transformer using formula equation. GP equal NP over NS times G of the impedance of a secondary. For the circuit so, okay, GP equal 5.53 divide 1. Okay, supposed to be square on this formula. I forget that. I'm missing square here. Okay. Then times 4 ohm. That given you 50 ohm. Okay. And now you want to calculate the power of the load. Vs squared divided Rm. 1.414 square divide 4 ohm. That given you 500 milliwatt. That is the maximum power at the output here. Okay. Now, a little more here. If you want to calculate the required turn ratio, that means you want to calculate the turn ratio here. To transform an 8 ohm resistive load in a secondary of, I'm missing, of
OF.
1 kilo ohm in the primary. They want to calculate the required turn ratio NP over NS. NP over NS, you get the square root of GP over GS. And that will be take the square root of 1 kilo ohm divided to 1 ohm. So they give it to you. This is the ratio. Okay. Now, but this one is no important to you. That's a designer. They want to design something. Okay. And they want the matching for the load using the transformer. However, we not design anything. Okay, so any question on the transformer? Only thing is, I want to make sure you're looking into the transformer. You know the primary voltage or you know the secondary voltage. Okay, and you know the turn ratio for primary and the secondary. Okay, so if the voltage primary higher than the secondary, that's what they call a step down transformer. Or if the secondary voltage higher than the primary, that they call a step up transformer. Okay. And also make sure you know the center test transformer. They basically divide secondary into two parts. Okay, the value will be a secondary voltage divided by 2. That means they same voltage. Only thing is the first and the second will be opposite. Okay? Any question about the transformer? That one is if you're looking through it, that will be help you a lot when you're working on the transformer in the left volt. Okay?
Okay.
Okay. If we not, then now we can get another handout for today. Okay, that means, let's see. LV, okay, band pass and band stop filter. The thing is on the textbook, not much information. So that's why, to understand a little more, I using left volt. That means when you're working on band pass filter or band stop filter in a left volt, you will go through that thing. Okay, so various combination of inductor, capacitor, and resistor can be used to produce low pass, high pass, band stop, or band pass filter. Band pass filter and band stop filter select a specific range of the frequency. The type of the band pass and the band stop filter studied in this unit is resonant circuitry. So a resonance in the AC, that's a very, very important to you. Okay, band pass filter can be implemented by connecting a series of parallel resonant circuit with the resistor. This combination forms a voltage divider across the generator. Okay, so two ways you can make a connection. L and C in series, okay, and series with the R. So basically, just a voltage divider, IC, HL, and R. Now, another way, they can connect R here, and C and L will be parallel, okay? Either one, they can connect either series or parallel. So when you're looking into this circuitry, then you can recognize that will be a band pass filter. Okay, now, this one I believe I already showed you. This is the stand for V out. Okay, so this is resonant frequency right here. You're going down. That's what they call FR, resonant frequency. What happened at the resonant? Happen is HL and HC equal. So they cancel out. So the leftover in the circuitry only resistance. Okay, so they get a maximum current. Okay, and not they say maximum voltage. However, if you're looking in here, this is a minus 3 dB. cutoff frequency. Okay, so at the cutoff frequency, they will be down to dB. And in this case, they get 2 points right here, one in here, one in here. So one they call F1, lower cutoff, and another one will be F2, higher cutoff. So if you want to calculate the bandwidth, then they will be equal F2 minus F1. Okay, a band pass filter allows a narrow band of the frequency to pass, but they reject frequency above and below that band. That only telling you any signal between F1 and F2 can be passed. Okay, outside F1 here or F2 here, they will be attenuate or reject. Okay, so pass band will be from F1 to F2. Stop band will be over F2 or less than F1. The range of frequency passed by pass band filter is the band width, which depends on the upper F2 and the lower F1 at the cutoff frequency. So when you're looking into this display here, and you must understand this is the output of the band pass filter. Normally, when you interview, they're not asking you more calculation, but they're asking for your understanding. Okay? Sometimes they can ask you what is the bandwidth from what to what for this display. Okay? So, band pass, they allow only the signal with the frequency higher than F1 and less than F2 to pass. Any frequency less than F1 or higher F2 will be stopped. If you get any question, okay, and go ahead and ask. I will try to see I can answer your question. Okay, any question up to this point? Okay, if it's not, the center frequency, that means FR right here, resonance, of a band pass filter equal what? Cutoff frequency or equal resonant frequency?
Resonant frequency.
Resonant. Very good. Okay. So basically, resonant frequency, that will be a center frequency for band pass filter. Like band pass filter, this is talking about band stop filter can be implemented by connect a series of parallel resonant circuit with a resistor. Okay, so now you get an IF series LC, or you can get LC parallel, then series with R. So only thing I want to make sure when you're looking into the circuitry, you know what is the name of the circuit. They don't care anything else, but they care what is the name of that circuit. Then this is band stop filter. Either you connect LC in series RLC in parallel. Now, this is the output of the band stop filter. Okay, you can see this is the V out. Okay, they going down this way. Now, basically, band stop filter, that's only telling you any signal higher than F2 or less than F1 to pass. Okay, any signal between F1 and F2, they want to stop it. So basically, this filter just the opposite to the band pass filter. Okay, a band stop filter or band reject filter reject a narrow range of the frequency but pass the frequency above and below that range. Okay, the range of the frequency rejected by a band stop filter is the band width, which depends on the upper and the lower cutoff frequency. Okay, however, I want you to understand for band stop, okay, any signal higher than F2, less than F1, able to pass it. But any signal between F1 to F2, they want to stop it. They just opposite to the band pass filter. Okay, so now they given you two output display, one for band stop and one for band pass. Okay, resonant band pass and band stop filter select a specific range of the frequencies. A high circuit scale result in which range of bandwidth A or B. High Q or low Q. Now they say high circuit Q results in which range of a band pass. That means they're telling you they get a high Q. Then what the range for the bandwidth? You can get a narrow band and a wide band. Which one?
Narrow band.
LB.
A.
A.
The answer will be A. You want the narrow band, you don't want the wide band. Last time I already telling you. Wide band you can make noisy. Okay? If you get a good Q, then they will be in a high band. Normally Q less than 10, that means low Q. Higher than 10, that will be high Q. Okay? Again, the answer will be A. Okay, in this band pass circuit, a series LC resonant circuit is connected in series with R. The input voltage applied this voltage divider. Output is taken from resistor R. I total before equal V generator divide to R. Okay. The thing is at the resonance, HC, HL equal, so they cancel out. Okay. You get left over the circuitry on the R. Okay. In order for you guys to understand a little more, when you tune your radio, that means you change the value of L and C to make sure they equal in order to get the maximum power. Okay? At the resonant frequency of this series, RLC circuit, the inductive HL and capacity HC reactive cancel one another, leaving only circuit resistance to oppose the current flow. I think the left one, they did very basic, very good job in order to technician. Okay. At series resonance, the circuit current is A, maximum, minimum.
Maximum
LB,
A.
A. Okay. That means HC, HL cancel. You get only R. That resistance. Okay. So the answer will be A. The response curve shows that the output voltage Vout is maximum at the resonant frequency FR of the bandpass filter circuit. This point equals center frequency. Basically, that is resonant frequency. The center or resonant frequency FR during do calculation equal 1 over 2 pi square root L times C of the bandpass filter circuit cell equal which one you guys doing for me, A or B?
Mr. Pham, is that nano or milli Henrys?
See, 10 millihenry,
Oh, 10 million.
0.01 microfarad.
The answer is B, 15.9.
Perfect. The answer will be B, 15.9 kilohertz. Try to go over the transformer handout and the bandpass stop filter handout. That will be help you speed it up a lot while you doing your left vote. Okay. So the thing is, I will be let you guys know who will be on what left phone station, what time, what the circuit board you're working on. Okay, so that will be when you get all of that done, then I will be make that certificate for completion for you. Okay. If you're not done, you're still there until you complete it. The thing is, when you're working on the left phone, whatever you do it, they record it into the system. So the lab instructor look into that and they know which one you complete, which one still not done. Okay, that automatically in the system, they take care of that. So that's why when I give you name on what day you're working, what lab you're working, what board you're working, and also given you your the part code. That means the code for your inside the system. Okay. So get any question up to this point? If it's not, I will be stopped at this point and will be continuing on next Monday. Okay, so you get any question, anything?
Thank you, Mr. Pham. Thank you very much.
Thank you, Mr. Pham.
Yeah, no problem. That is my job, okay? I like to helping your guy to be a good technician. That means you have to understand at least the basic. When you see the transformer, when you see the output of the low band pass filter, low pass filter, or band stop filter, you don't know what is, and it's hard for you to get the job. On up the calculation in detail, you don't care. But the thing that we study, so that's why we have to do calculation. Okay? So, good night.
Thank you, sir.
Good night.
Good
Thank you. Good night.
night, everybody.
Good night.